This is the second in a series of videos about intermolecular forces. We're going to talk about dipole interactions and hydrogen bonding. So the second strongest of the intermolecular forces is dipole interactions. These forces are present in molecules that have permanent dipole moments. So when we talked about dispersion forces in the last videos, those were examples of instantaneous dipoles and induced dipoles. So they were only there for a fraction of a second. This type of interaction, on the other hand, only occurs in molecules with permanent dipoles. So the dipole needs to be there all the time. And a result of this force is it causes the molecules to line up, with positive associating with negative. So we call that head to tail, is the way they get in line. So let's look at a picture of what that dipole force might look like. So we drew sort of like a distorted looking sphere in the last video, and we'll do that again here, but we'll go one step further and give it a little bit of color. So when you have a dipole, you have one part of the molecule that's slightly more positively charged. So this is a lowercase delta, meaning a partial positive charge. And we have the other half of the molecule that has a partial negative charge. And the way these molecules line up is positive is attracted to negative. So next to the negative side of one molecule is the positive side of another, with its negative side facing away. We can draw the dipole interaction as a dotted line connecting the opposite charges. So they can line up head to tail in this way, or they can interact in more of a side-to-side orientation like this. But it's the same in both cases. The negative is always attracted to the positive, and they prefer to line up next to each other in that way. And so we could draw the dipole interactions between each pair of negative and positive, like so. So just like we asked ourselves for dispersion forces, we need to ask ourselves, what affects the strength of these forces? Are some dipoles better than others? And the answer is yes. The greater the difference in electronegativity, the greater this difference in charge is going to be. So electronegativity, or EN for short, a greater difference in electronegativity is going to cause a greater dipole interaction. They're going to be this partial charge is going to be larger and larger depending on the difference in electronegativity. And as we said for dispersion forces, the proof is in the boiling point or the melting point if you want to compare those. So let's compare the boiling points of two molecules that would have similar dispersion forces, that have similar size and similar shape. So we'll take HCl against F2. So according to the periodic table, both of these have a molecular mass of around 40 grams per mole. So they're about the same size, and they're both linear, so they're both the same shape. But let's look at the dipole and see how that's different. In the first molecule, hydrogen is very electropositive, chlorine is very electronegative. So we could draw in the dipole arrow like so, pointing towards the chlorine. Whereas for the fluorine, this bond is between two identical atoms, so there is no net dipole in this molecule. And so if we see the strong dipole here in this molecule, a strong intermolecular force holds those molecules together, makes it more difficult to boil and to jump into the gas phase. So we would predict there would be a higher boiling point for this one than for the fluorine. And if we check the empirical data, we see the boiling point for this is 188 Kelvin versus fluoride, which is 85. So indeed, the stronger the electronegativity difference, the stronger the forces holding it together, and the higher the boiling point. All right, the next one is hydrogen bonding, which is the strongest type of intermolecular force that we have, but still is not actually a real bond. So hydrogen bonding is present in molecules which have hydrogen, obviously, but it's a particular flavor of hydrogen. It's a hydrogen that has to be bonded to something very electronegative. Has to be bonded to either an oxygen, a nitrogen, or a fluorine atom. And so what this is, hydrogen bonding is kind of just like extra strength dipole. Because if you think about it, hydrogen bonded to something very electronegative is a dipole. It's a very, very strong one, the strongest one you can get. Because this is the largest possible difference in electronegativity. So just like extra strength Tylenol, we have extra strength dipole interactions, hydrogen bonds. So let's play a game called, is this an H bond? Is this hydrogen bonding in the following examples? Excellent test question right here. All right, here's methane. Here is a molecule. We can see that it has hydrogens in it. Is this bond with the arrow a hydrogen bond? And we see that it has a hydrogen, but we know that hydrogen bonds have to be in between hydrogen and something very electronegative, and carbon is not. It is not a great enough difference. So the answer is no. Got too excited there. No, it is not a hydrogen bond. Let's try another one. Here's a bigger molecule. This one does have an oxygen in it. How about this bond? Is this a hydrogen bond? It is a bond between a hydrogen and an oxygen, but remember that hydrogen bonding is an intermolecular force and needed to be between one molecule and a completely different molecule. This is not a hydrogen bond. This is an actual bond between a hydrogen and an oxygen. This is an intramolecular force. If we wanted to see an intermolecular hydrogen bond, we would need to see this hydrogen bonded to an oxygen associating with an oxygen on another molecule. So we can draw another of the same molecule over here. And so this interaction, rather than a real bond, between a hydrogen that's on an oxygen and an oxygen that has a hydrogen, this is a hydrogen bond. So remember not to be tricked by actual bonds within a molecule. We're talking about associating multiple molecules together. All right, one more. Here's a water molecule. Water can form hydrogen bonds, but it isn't these. It's between one water and another water molecule. And so every hydrogen can donate one hydrogen bond to something, and every oxygen can accept two hydrogen bonds. It can accept one hydrogen bond with each of its lone pairs. So these two could be associating, and this could be associating to something else that I didn't bother to draw, and the same for this one, and the same for this one, and on and on and on. You can see that hydrogen in water is the master of hydrogen bonding. And this leads to several other super cool properties that we're going to learn about later. So this interaction between a hydrogen bonded to an oxygen in one molecule and an oxygen that has a hydrogen in another molecule, that interaction is hydrogen bonding. Okay, and what affects the strength of these? you could probably guess. What affects the strength of the hydrogen bonds? It's the number of locations where a hydrogen bond can be formed. So it's the number of hydrogen bond donors, where the donor is the hydrogen. So this molecule that we drew had one hydrogen that could donate, whereas in a water molecule, there are two hydrogens, and each of those could donate a hydrogen bond. So this one has the stronger hydrogen bonding strength. And as usual, the proof is in the melting and boiling points. So let's pick something where we should clearly be able to guess the winner based on our previous amount of knowledge. So here's a pretty small molecule, ONF. Its molar mass is 49 grams per mole. Here's an even smaller molecule, a water. So if we hadn't yet learned about hydrogen bonding and we were only making our guess on boiling point based on what we had learned before, we would guess based on dispersion forces. Since this one is much heavier than this one and much larger, we would say this one should have the strongest dispersion forces and the highest boiling point. But what we discover is that this one has the lower boiling point and water has the higher boiling point. In fact, they're so different that this compound is actually a gas at room temperature, whereas water is a liquid. So how can we explain that? If the dispersion forces predicted that this molecule would have the higher boiling point and it actually has the lower, then we need to think about something else. We need to think about the hydrogen bonding, the extra strength dipole present in this molecule. So we could draw a slight dipole in this molecule because fluorine is slightly more electronegative than the other two, but it would be a pretty small one because these are the three top most electronegative elements that we know. Whereas in hydrogen, oxygen is the top electronegative element, one of them, and hydrogen is one of the smallest. So this dipole is going to be very much larger. So there's a much stronger dipole moment, and this is a very important, very strong intermolecular force that holds these molecules together, and it keeps them from boiling into a gas at room temperature. So by now we've learned about several different types of intermolecular forces, and you're probably saying to yourself, which one of these would win in a fight? If I have all of these forces to consider, how do I know which one is the most important? And it depends on how heavy your competitors are. So which of these three forces is the most important depends on the molar mass of the compounds. So if your molar masses are similar, you have a number of small compounds, they have like 6 atoms or less, mostly top 10 elements, then we're going to go based on the ranking we drew in the first video. So your hydrogen bonding is going to be the most important force that you consider. Then the dipole moment is the next important force. And if there's nothing else to help you decide, you can look at dispersion forces. Hydrogen bonding will be your most important indicator of the strength of those forces. On the other hand, if the molar masses are different, if you have something very large compared to something that's very, very small, then the type of force that depends on the size, the dispersion force, is going to be your most important dominating force. So let's try that out in this example. So here we have 4 small molecules listed, molecules A, B, C, and D, and we are going to try and arrange these liquids in order of increasing intermolecular strength. So the first thing we can observe here is that the molar masses are similar. And if the molar masses are similar, that means we care the most about hydrogen bonding, more than any of the other forces. So we should have a look at the three types of intermolecular forces and figure out if those forces are present in each of these. So we'll make a little table here: dispersion, dipole, and hydrogen bonding. Now let's check off if those forces are present in each of them. So we'll start here with molecule A on the left. Everything has dispersion forces. So we'll just go ahead and check that off for everybody. Dipole forces, we can see that we have some pretty electronegative atoms on this right side of the molecule, sort of near the top. So there is a dipole. This one has an electronegative atom near the right side, so there is a dipole. Sulfur is right underneath oxygen in the table. That's a fairly electronegative atom, more so than carbon. So that's going to have a dipole. And this one has an oxygen on the right side. That one's going to have a dipole. So we're neck and neck here in terms of forces. So now let's look at hydrogen bonding. This is going to be an important one. So look at how many hydrogens are eligible for hydrogen bonding. This hydrogen is bonded to something very electronegative, and so is this one. So there are two possible hydrogen bond donors in the same molecule, just like in water. In this one, we have one hydrogen bonded to an oxygen. In this one, we don't have any. Sulfur is not electronegative enough to count. And over here, we've got a hydrogen on an oxygen. So finally, we're starting to see a difference that'll help us make our decision. So similar molecular mass, the hydrogen bonding is going to be the most important deciding factor. So we'll start with that. So we're going to rank them from weakest intermolecular force strength to the strongest. Okay, so there's a couple of things that stand out right away. The first is this big X. Everything else about these molecules was the same, except for molecule C did not have any hydrogen bonding. So it's missing that force, and that's going to mean its intermolecular forces are the weakest. So we'll put that at the bottom. The other thing that stands out for me is molecule A had 2 hydrogen donor sites. And we said hydrogen bonding was the most important thing that we cared about, and this one has twice as many opportunities to do that. So it is going to be the strongest. Molecule A. Okay, so this one has no hydrogen bonding. And this one has 2 hydrogen bond donors. So now we have to look at our last 2 molecules, molecule B and molecule D. We can see that they both have hydrogen bonding with 1 hydrogen donor, so that's about the same. If we look at the dipole, they're fairly the same strength, pointing in the same direction, so we're left with dispersion forces. And dispersion forces are greater in the heavier one, and we can see that molecule D is bigger than molecule B. And if you are bigger, you have more dispersion forces, you are going to be stronger than the other. So molecule D is going to be greater than molecule B. And that is because they have similar hydrogen bonding, and they have similar dipole moments. And so when it came down to dispersion, this molecule was lighter and this molecule was heavier. And that's what we use to help with our ranking. So for these small, similarly sized molecules, the hydrogen bonding is the most important. If we were to compare molecules that were very, very different, the dispersion forces would be our champion. And those are the forces that are going to help us determine what the phase of a particular compound is going to be at some given temperature.